Okay, I'm going to share a screen now, and we're going to see the second part of the CPU design in advanced computer engineering, now being called parallel processing by Jonathan Freaney and Ethan Schneider, computer engineers of 2020. Go to it off the website instead of a specific syllabus, since this will live on beyond courses. And sample projects here. This was CPU. So this is piggybacking on the previous video. I'll put a link in the description on the YouTube channel to the previous one. And then this is 1B, which is their final presentation of this project.
For our project and final lab, we built an 8-bit CPU. And before we get into the actual circuit and the simulation, and just to give a bit of context for the design, I'll quickly go over the instructions that we used. So our assembly code follows the general structure seen here of a mnemonic command, followed by the operands and then the destinations. And our instruction set contains about 65 different opcodes. Our instructions are all 16 bits wide and follow one of these 4 formats, which you can take a closer look at if you want. And here is an example of a small program that will just loop infinitely, and then what it will assemble to. And then we'll show this program running in our CPU a bit later in the video. This is our main circuit of our CPU. We use a word size of 8 bits. So our memory down here is 8 bits wide, and we have 256 addresses. All our general registers are also all 8 bits, and we have 8 of those. Then we have some special registers up in the left-hand corner. We have the instruction register that stores the current instruction, program counter, accumulator, a secondary just B register, and then our flags register. Right below that, we have some bus control. It's basically just controls inputs to various components like the general registers and the memory and the special registers. And then over on the right, we have our code memory where we store instructions to be executed. And our instructions are all 16 bits wide. And then we have the ALU and the control unit and our clock down in the right-hand corner.
Yep. And it's worth noting, this is probably this is not a von Neumann architecture. The size of the code and data are separated into 2 different regions of memory, and they're not even the same size of words. So it's a little messy, but it works. So briefly go over the ALU. I think at this point, anyone looking at a project as complex is probably familiar with the basics of building an ALU at this point. It just does arithmetic and logic. This one just does a few operations like addition, subtraction, multiplication, signed multiplication, division, and signed division, basic logic operations and shifts. Takes 2 inputs, X and Y, and an opcode to select between the results and the current flags register. We've only used the the high 4 bits of the flags register, so we just pass on the first 4 bits as if nothing changed. And then there's actually 2 outputs. Most operations will only use 1, but some of them, specifically the multiplication and division, use 2. That's because multiplication requires twice as many bits to store the output. So the high bit of multiplication is stored in the B result, which later gets stored in the B register. And for division, there's also a remainder that is stored in the B register. So that is the entirety of the ALU. For the control unit, we kind of cheated our way through this. This is interesting. So the control unit stores and maintains the current phase of the machine instruction cycle. Due to the initial design of this, we only actually ended up using the first 2 phases. Everything fit in there, which is pretty cool. I probably could have reduced that to just 2-bit counter here. We could have used Logisim's built-in counter, but that took up way too much space in the screen, and I didn't like that. So we're using a register and counting ourselves. It also takes in the current clock value and the current instruction, which is stored in the instruction register here. The control unit can specify using this right here, that output, whether or not to actually write to the instruction register. And it also takes in the current flags. So all these outputs over here are used to determine what memory is actually moved around to where. So those will come out right here from the control unit and determine which of these are sending data to which parts of the CPU. Within here, yeah, again, we cheated our way out of this. This programmable map stores 32-bit words. There's 256 of them, 1 for each possible opcode. We've only utilized like 60 something of the actual opcodes you could have out of 256. So, and that was kind of efficient, but also we still have a lot left to use. So the way this works is we were really lazy. And we specified this in an Excel file, which I know is like gross, but so this specifies everything we need. At the top here, we specified the amount of data each one of these things is going to take up in this row. There's the bit widths of those data items. And each one of these columns stores information such as the corresponding ALU operation for the instruction, which data item to select for the inputs for the operation to the ALU, and other things. Usually things that end in an S select the data item that will go into some kind of register, and things with an E on the ends are for determining something more like whether or not you're allowed to actually write to that register. So we have quite a few things in here. I'll go over an example in a little bit. This thing gets compiled by Python code. Yeah, that I don't have up right now. For very large assembler, which was we have 2 versions, one of which Ethan wrote, which is pretty nice and got us testing much faster than this one did. This one's a little bit cleaner, but they both work pretty well. So we take that and we can load that in here by just right-clicking on this, hitting edit content, open, and then we just take our map, which is located somewhere in my computer if I can actually find it. Programmable map, and we can just open that up and it will load into Logisim. And so that gets each word, which depends on the current opcode, which is the first byte of the instruction, is used as an address into the programmable map, which is then split up into all these different outputs that are then sent out. The immediate value, which is also part of the instruction, is also split off here, as well as any register indexes, if there are any for an instruction. And though they're also sent out as outputs. So right now we have a simple program loaded into here, which is an infinite loop. Here's an example. This just moves data items around. We're not using the ALU here. This simply begins by moving the preparing the upper part of the PC by moving 0 into the accumulator, then moving the accumulator into the 0 register. And then it also moves 0 into the accumulator register, which effectively sets up an address of 0, which is the beginning of the file here. And then we proceed to jump to that address here, which jumps us back to the very beginning. So I will just run this program. This is already loaded in here. You can see the instructions here coded in hex. They only each take up 4 digits in hex here. So simulate. We're running at 16 hertz. Enable ticks. There you go. You can see it running. Each time it just jumps right back to the first part again. It is worth noting, you'll see it temporarily flash down to here. And the reason for that happening is that every time we get to the fetch instruction, it automatically increments the counter to the next point in memory first. And then when we get to the actual decoding phase or whatever comes next, it is then moving us back to something else. But that's why it temporarily jumps down there.
Okay, some quick comments on that. So there was a little redundancy there to what they had shown. Their progress report actually was almost a complete project. They show how they use that spreadsheet to come up with a code that's essentially the microcode inside the control unit. And that's not an unusual thing. You either have a programmed control unit in the CPU or hardwired. Now, if it was hardwired, which happens nowadays for speed, or it did for a while in the first RISC processors, but never so with the sys processors or the large computing systems like I worked on in IBM, because people expect you to be able to change the microcode. So it's not an unusual thing to have actually a code like that for each instruction that's actually executed by a separate tiny little finite state machine inside the big control unit, not the main one that does the pipeline, but one that sequences through the microcode. Also, the Harvard architecture, as they mentioned, is a microcontroller kind of thing with separate program memory and for data and program, and that's for inexpensive little applications where you burn your code in after development for a microwave or a refrigerator or a fuel injector, and then your data needs to change. And then the I/O that was mentioned in the first video of not being there really is because this memory mapped in microprocessors and microcontrollers. So you really just need to write to a certain address. So even your ports, your 4 ports on your microcontroller in P0 through P3, they're all memory mapped. So essentially just write to them. Now there is of course some electronics you need to work out with pull-ups and things to make the signals work and make sure you're not reading from the buffer instead of a pin. There's a number of little things. But this is a very complete, very thorough project for a simple CPU. Now it doesn't have a floating point unit; it's all integer, of course, and that this is the level of complexity that you hope for in a class like this. And, but again, it was probably much more than most people would ever do. And then his senior project we'll look at with Jonathan. He did a GPU spinning off of what he's done here. We'll look at that in another class. Okay, I'm going to end this video.